This is Algebra 2 at Trig, Unit 1B.1b. We're talking more about the graphs of vertex form. We know that vertex form would look like y equals a x minus h squared plus k. That's our typical format of our vertex form. When we look at the quadratic function in a table, we know that the second difference is going to be a constant number. The second difference is going to be a consistent value in each of our tables. There's a bit of a video here that you can click on and you'll see a bit of what we're talking about. The vertex is the point. When we look at a table, we're going to see matching pairs of y values. So if we look at one of these examples down here, we see the 3.5 and the 3.5, the 5 and the 5. We have matching pairs of y values. The vertex is in between those matching pairs of y values. It's between those matching pairs. The vertex will be the h and the k of the equation. So once we have the equation, or if we had the vertex, we could start to write the equation, knowing the h and k values. The a value is going to be half the value of the second difference. So that is, we've talked about the second difference in the past, but we have not talked about how the a value is equal to half of it. All right, so this is the first time that we're going to use this common difference. And to use it, the a value is going to be half the amount. So we're coming down here. First of all, we find our values that are the same. And that puts the vertex right in the middle. So our vertex is 2, 3. What we don't know is what the equation is, or what the a value is specifically. There's different ways we can do this. We could use this whole second difference concept. That works. Now, the way I'm going to talk about the second difference this time, I'm going to talk about how far are these numbers away from each other. All right? They are 3 numbers away and a half. So it's going down to get to that point. So we're going to call that negative 3.5. And from these two, this one would be negative 2.5. If we look at the distance apart from these, this is still going down, so we would call it 1.5. This one is negative 0.5. Now we start to grow. We go up 1.5. We notice that those numbers are not a consistent value. So now we're going to look at the distance in between these. From negative 3.5 to negative 2.5, that is an increasing value of 1, 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 and an increasing value of 1. So we have the second common difference between each of the values. So what that tells us is our common difference is 1. So our A value is going to be half of 1. So our A value is going to be a half. Now let's be sure that even makes sense. When we look at the points, in the long run, the graph is going upwards. So we know that it's going to be a positive. That helps support that. We typically would go over 1 and up 1, but we're going over 1 and up a half. We typically would go over 2 and up 4, but we're going over 2 and up 2. So that's making sense. That's half the amount. So you should be able to make those comparisons by looking at your table to what you already know. So we have y equals half x minus 2, because you know your vertex is at 2. It's 2 comma 3. So it's x minus 2, it's always the opposite, squared, plus 3. So your axis of symmetry is an x value, and that's going to be at 2. It's where the vertex is at. Your line of symmetry always includes the vertex. Your domain are all real numbers. You can plug in any number into your equation of a quadratic. Big number, small number, maybe not imaginary, but we'll hit those in the future. Range. Your range has to do with your y values, has to do with the k. So it's going to be greater than or equal to your k value because we are increasing over time. So its y is greater than. It's always your k. That's our lowest value. Your k value is always going to be either your minimum or your maximum of the function, of your quadratic function. Your end behavior. As x heads negative, if you look at your graph, as x heads to the left, where are the numbers going? The numbers are going upwards. So your graph, your function, is going to infinity. As we move to the right, as x gets bigger, you can see slowly but surely the graph is increasing. So it's going to infinity. Your end behavior looks at the x value as it gets really small. What does the function do? And as it gets really big, what does the function do? Transformation. Because your equation does not have a negative, we do not have a reflection. We have a vertical shrink. By a scale factor of a half. And we have a translation it's translated two units right and 3 units up. So you should be able to put this one together. Go ahead and try to identify your vertex, figure out your second common difference. How does that help you determine your equation and build from there? So when we look at our tables, one thing we can take a look at is we can do the subtraction of negative 44 minus our negative 23, which is adding our 23, which would come out to be negative 21. This minus a negative 8, which would be really a plus 8, would give us a 15. This minus this would give us negative 9. This minus this would give us negative 3. This minus to this would give us 3. This minus this would give us 9. Now notice that our change of positives and negatives is happening right here at the vertex. That's not a coincidence. Look at the 1s. They're the same on both sides. The 8s are the same on both sides. So that helps highlight where our vertex is at. If we do our common difference again, all right, you could either do the subtraction game like I just showed you, or if you just like to talk about the distance between them, the distance between them, we're going down, is a negative 6. We're going down, which is a negative 6. We're going down, which is a negative 6, a negative 6, a negative 6. Or you could say negative 21 minus the negative 15, which means add 15, which is negative 6. And you could build it that way, however you like to think about it. So you know that your A value is going to be half of your second common difference. So we should be half of negative 6, which is negative 3. So our equation is going to be negative 3x plus 3 squared plus 4. Because our h value has to go into our equation as negative 3, so x minus a negative 3 is a positive 3. Axis of symmetry is going to be at our h value. Our domain is all real numbers, and our range is going to have to do with our k value. Because it's opening downwards, the y values are getting less than or equal to. The end behavior, as x approaches negative infinity, our function is, looking at your numbers, it's going small. It's going to negative infinity. Good. And our transformation, because our equation has a negative value in front of the r, we are reflected over the x-axis. We have a vertical stretch by a scale factor of 3. And translated, 3 units left, 4 units up. Now we're going to write an equation. Write a quadratic function that is narrower than the parent function. Okay, let's see. To be narrower, you have to go up faster. So that means that your a value has to be greater than 1. And has a domain, of course it has a domain of all real numbers, all quadratics do, so that doesn't tell us anything. And a range that goes from negative infinity up to negative 5. That was a common mistake on the quiz, to write this in the correct order. Negative infinity has to come first. The smaller number has to come first in interval notation. So one way you could do this, if you want it to be narrower, you need to pick a number that is bigger than 1. Any number bigger than 1 will do. I picked 5. X squared. I'm not going to talk about a translation right or left, so I don't need parentheses. It doesn't talk about that. So it would be common not to use that. And then, of course, we're doing our range all the way up to 5. And in fact, it's up to -5. So this has to be a -5. And since the range is negative infinity, we have to have a negative in front of our a value. So that's going to have to be a negative in front of the a value because the range goes from negative infinity up to -5. So we go to our next one, and we're going to create a quadratic function. What does quadratic function mean? It means it's going to be x squared. It's going to have a vertical shrink. That's an a value that is smaller than 1. It's going to be translated left, so it's going to be x plus 8. It's going to go left 8, so it's going to be x plus 8. And it has the end behavior that is x gets big, it goes up, and when x gets small, it goes up. So the a value is positive. So the a value is going to be positive, so we'll call it 2/3. Any fraction will do. Any fraction less than 1 will do. We are going to translate left 8 units, so this has got to be a plus 8 because -8 in there would make your 0. But there is no information about the range. There is no information about a translation vertically. So leaving it there would make sense. And what we're going to finish our little time with is a little bit of an activity here, trying to figure out our equations. You can do this a couple different ways. You can look at your equation and then try to find it in the given information. Or you can take the given information, write an equation, and then find your value up top. So for example, this is a parabola with the vertex at 0, 0. So it could be E, it could be F, it could be D. Those are all somewhat reasonable options. This might look like at 1 it goes up to 5. So this looks like it gets stretched up by 5. So I'm going to fall for that as being E. This is graph E. It has a vertical stretch by 5. It definitely was not following the pattern of vertical stretch of 1. This has a vertex at 4, 3. So I need a quadratic that is x minus 4. Here's one. There's a good chance it's that one. It's not absolute value. It's not absolute value. It is up. So yes, this has to be B. And you can work your way through some of this. All right, this one seems to be negative. Okay, it's a quadratic that's negative. At 2, it seems to be going up to about 4. All right, but that doesn't seem to match. as we look at number 3, f is the only one that makes sense, being a negative x squared, but I don't see that as being when x is 1, y is negative 0.5. Nowhere close to that. So we're going to hold off on that particular answer. Let's move on to another one and work your way through these. So as we look at the letter J, we see 5x squared minus 6x squared. Those units are the same. 5x squared minus 6x squared, so that is just negative x squared. So that's what we were talking about. This is what we knew this was. That's J. Here we're going up 4. It's a quadratic. It's going straight up 4, so that's going to be H. Over 1, up 1, over 2, up 4. So this looks like I, which is going to be x squared. I times I is x squared. Here we're over 4, maybe down 3. To the right 4, down 3, that looks like K. Then to talk about our tables. If you're going to do a subtraction game, you can work from the right-hand side. Maybe different than I told you in the past. But we notice that 8 minus 7 gives us 1, and this minus this gives us 1, and 1, and 1, and 1, and 1, and 1, and 1. We have a y-intercept at negative 4. So we have a linear equation. Actually, our y-intercept's at positive 4, so that matches here to be A. The y-intercept is where x is 0. That's 4, and that's what we get for our linear equation. One, 1. This minus this is negative. Oh, look at this one. This is subtracting. Positive on this side, negative on this side. That tells us that this is an absolute value. All right, it's an increasing on the end, so you know it's a positive absolute value. The vertex is going to be here at 4, 3. Three and 4. Nope, actually the 4 and the 3 is our vertex. We have an absolute value, so it's going to be x minus 4. So it looks like the letter C. So here, when we're looking at our values, we know that this is 5 apart, but getting smaller. This is 3 apart, getting smaller. This is 1 apart, getting smaller. This is 1 apart, getting bigger. 3 apart, getting bigger. So those are not all the same common difference, so we're going to try it again. These here are 2 apart, getting smaller. These here are 2 apart, getting smaller. Getting bigger, getting bigger. So it looks like we're going negatives to positives, which is going to make this an absolute value. And where the numbers are the same, this would be our vertex. So looking up at our answers, where this is translated to the right 4 units. looking at this over again, this minus that is negative 2. Negative 3 minus negative 1 is negative 2. Negative 1 minus minus 1. So their distance is negative 2. All right, we're going to start this one over. Sorry. We agreed that we were down by 5, down by 3, down by 1, up by 1, up by 3. This one is up by 2. If you think about the number line, negative 5 is smaller, negative 3 is bigger. Up by 2, up by 2, up by 2. This is not absolute value. This is quadratic. All right, quadratic, the a value is going to equal half the value of our second difference. So the a value is going to equal 1, and it's going to be moved 4 to the right. So this has to be g. So this is getting larger. From negative 20 to here is a distance of 15 positive, a distance of 5 positive, a distance of 5 negative, distance 15, 25, 35. All right, so now we look here and we see that the distance is going down by 10, down by 10. So there's our second common difference. This is quadratic. So our a value is going to be half of our second difference, which is negative 5. And our vertex is going to be at 0, 0. So I see this as letter F. This is increasing by 1, increasing by 1, increasing by 1. If we were to decrease 1 here, we would decrease 1 to be at 0, 0. So this is y equals x. The y value equals the x value every time. Here, we're going down by 1, we're going down by 1, up by 1. Our common numbers make this a vertex, so I see this as an absolute value. See if I don't mess this one up for us. So I see negatives on one side till we get to our absolute value, and I see it's decreasing to this point, then it's increasing, so that seems like absolute value. So it's absolute value that should be L. There you have it.